From movement to medicine, climate change in our future, everything depends on energy. We use it to drive us, we use it to heal us. This is The Coefficient Life, and we sit down with the smartest scientists, futurists and thinkers on the planet to discuss the big ideas around energy in all its forms and ask the questions you wish you could ask them. I'm your host, Anthony Salomon.
And I'm your other host, Kim Brooks. Anthony and I are here to bring you stories that are shaping the future of our planet. Now let's dive on into a universe of energy.
From the Podcast Bureau, this is The Coefficient Life. We're going back to the moon and then on to Mars. That's right, with breakthroughs in propulsion, technology, and more, we are going back to the stars and in a big way. Dr. Dan Kotlyar is part of the team that is going to make this happen. Dan is an assistant professor in the Nuclear and Radiological Engineering School of Mechanical Engineering and is the recipient of the NRC Faculty Development Fellowship. He is one of the top minds in fuel depletion and advanced reactor systems, and he believes profoundly in education through research. Dr. Dan is also the guy building the engines for NASA's planned moon base and manned missions to Mars. And today, we had the opportunity to sit down with him to discuss what it takes to get to the moon, Mars, and beyond, in what we hope is the first of many conversations with Dr. Dan. He gets us excited about particles and propulsion that are ready for spacecraft and celestial bodies.
So I'll let Anthony...
Well, I was going to say, do I detect a Hungarian accent?
Well, you detect a Russian accent.
A Russian accent. Russian accent.
A very strong one. Although I was born in the Soviet Union, but immigrated to Israel when I was a kid. So I spent most of my life in Israel. Unfortunately, my accent is very heavy Russian.
So my grandmother, Ukrainian.
Okay.
Went to Israel.
Okay.
My dad was born in Israel.
Okay.
And then I served in Tzahal.
Really?
Yeah.
So you speak Hebrew?
Not as much as I used to.
Okay, so where did you serve?
So in the north, in a base called Salmon.
Salmon?
Yeah.
Yeah?
Yeah.
Okay, that's cool. So this is a South African accent?
Australian.
Australian?
Yeah, so my dad moved to Australia, met my mum, had me and my brother, and I grew up between Australia, New Zealand, and Los Angeles.
That's cool.
So I have this weird accent that kind of people think it's South African.
I mean, to me, it sounds South African, but now Australian makes sense.
Yeah.
They are similar, right?
A little bit.
One's more Dutch influenced, I think, and there's more British influence.
Yeah.
Well, anyhow, much better than mine.
I wouldn't go that far. But my Russian is probably worse than my Hebrew, which is not saying much. I have a lot of Russian friends. So, of course, the first thing I learned to say was every bad word in Russian.
Of course.
And
they have a lot of those.
Correct. And some of them, when you say them, they don't even translate as something so bad. And then you go, but if I put it with this word, that's terrible.
Yeah. So we speak Russian. My kids, my son used to understand Russian really well. And then since I think the age of 5 or so, he switched to Hebrew. And ever since he spoke Hebrew, and then we moved to England first, to the UK, where we spent 3 years. And his English picked up with a very heavy English British accent.
Oh, wow.
Which was wonderful. My daughter doesn't speak Russian at all, and she barely speaks Hebrew, unfortunately. Very difficult, because, she used to speak 3 languages. She spoke Russian until she started very early. Like, she's very gifted in terms of languages, absorbs super quickly, like English. After a week, she spoke fluent English.
Wow.
It's unbelievable.
Unbelievable, yeah.
It's unbelievable, but I started to speak it when I was 3.5, and I was the wonder kid in my family.
That's awesome, yeah. Well, thank you for taking the time to meet with us today. It's great. I'm so fortunate that I'm getting to meet all these amazing people that are, really at the top of the field of what they do. And I don't know if anyone told you anything about what we're doing.
Very vaguely.
Essentially, Ken and I are doing a podcast called The Coefficient Life. And the idea of it is to change the conversation around everything nuclear, from energy to propulsion to everything, medicine, whatever it is. Because the thing that we have found, and I'm sure you find it too, is you talk to just the general public and they hear the word nuclear or the word radiation and they run in the other direction. They think it's the worst thing ever. They don't see a benefit in it. They think of every movie they've seen with every terrorist that's always after something radiological or nuclear. And then the only time when they think of energy, they think of all of the meltdowns that have happened over time or all of the big bombs that have been dropped. They never think of anything positive around the conversation.
Yeah.
So that was the idea, was to change the conversation around nuclear from, as I said, from everything from power to medicine. So yeah, and then we thought there's no better team of people to come and talk to, or at least get us started, than talking to everybody here.
So this is that a general discussion about my research or general discussion about nuclear energy? Or?
So at the moment, we would love to have a general discussion about two things, I think. One is your thoughts on the sort of the segment of the industry that you're in, and then specifically your research and what excites you about that, and what you're looking forward to in the future of that.
Yeah, maybe just a couple of words about my background. I think even when I originally started my research, it was most focused on fuel cycle analysis related to the use of the fuel inside the core and what happens to the fuel after it has been irradiated. Or I would say I didn't have too much in-depth research in that specific area, but when the fuel is irradiated in the core, eventually it comes out of the core, and eventually you have to store it somewhere for a long term. Long term is really long term in terms of nuclear. However, you don't produce a lot of waste. Like metric tons, you don't produce too much of it.
I was listening to something the other day, and they were talking about, like, if you took all of the waste from all of the reactors ever built,
yep,
it would only fill one American football field and only about 10 meters high.
That's it. Now, obviously, there are concerns about making sure, because you don't want to transport fuel, irradiated fuel from different parts of the countries through roads and so on. It is not very proliferation resistant,
mm-hmm.
But at the same time, it doesn't occupy too much space. And, I was recently in France in their facility where they store fuel, and those are like containers big. And it's one building of the entire fleet of all France nuclear power plants. It's unbelievable how small it is, honestly. So you are right. You don't need a lot of space. However, I was focused on a slightly different question. And the question is, the fuel is typically irradiated and it needs to be stored for hundreds of thousands of years, simply because if you want that fuel to reach the same natural radiotoxicity that exists in nature, you have to wait that amount of time. I was looking on ways to actually make this only hundreds of years rather than hundreds of thousands of years. Obviously, you have a lot of advanced reactors that are also looking on this. I was sort of looking on an intermediate step where you have, because advanced systems are something that will be built in the future, but they don't really exist nowadays, at least in massive production. So I was looking, how can we utilize our existing light water reactor fleet to essentially incinerate or deplete some of those long-term actinides that are produced in the reactor core. So that is my initial background. And while I was doing that, of course, you have to apply different modeling and simulation tools. And actually now I find myself mainly doing a lot of the modeling and simulation, less about analyzing different advanced systems. Unfortunately, I do want to do more about that as well. I have my own ideas, and I'll show you my projects as well and how we approach, advanced systems for the future. But at the same time, unfortunately, right now, I'm really more focused about the computational methodology evolving around, how you would create a safe system, or how would you increase the economic attractiveness of a system, for instance.
Yeah.
That's my main focus right now, is the computational efforts behind those systems.
When you're powering a reactor and you're using the fuel, how many cycles can you use that fuel for before it can no longer be used and it has to be treated as waste?
Okay, so typical and majority of nuclear reactors in the world are light water reactors, either pressurized water reactors or boiling water reactors. They typically employ what they call a multi-batch cycle, and this is simply to improve the utilization of the fuel inside the system. So typically this would be anywhere between 2 and 3 fuel cycles. So the fuel sits for 3 cycles, for 4.5 years in total, roughly, and then it is being disposed. But, the French, for instance, would then recycle that fuel, take the plutonium and minor actinides and mix it with the depleted uranium, for instance, and create a new form of oxide fuel, and would irradiate that again.
Just burn that in the reactor.
Yes, so the benefit exactly is, you produce more energy from the initial uranium. So if you start from mining that uranium, right? So you want to see how much energy is produced from that initial uranium. And obviously by recycling this again, putting this back into the system, you have 2 benefits. A, you produce more energy of that initial mass of uranium. And B, you essentially take those long-lived actinides and you burn them. So produce energy and reduce the waste. So that's
what I was saying. That's actinide burning.
So we were talking about
you can only do that if you know how to manipulate the neutron flux in the core.
Yep.
If you can manipulate that flux, you can put the flux where you want it to be, how it needs to be to burn those things.
Yeah. Now, they are doing this with existing light water reactor fleet. The whole point of advanced systems, or mainly when I say advanced systems, could be multiple systems. It's a very broad definition. But if you take a fast reactor system, where basically the idea is a fast reactor is operated on a slightly different physics. The neutrons there, you don't need to thermalize those. Okay, in a light water reactor, the reason we are using water is to cool down the system, but also to moderate the neutrons. And it's advantageous from the point of view of the physics. You sort of increase your chance of having a fission, and therefore you don't have to use a highly enriched uranium inside the core. So we operate our systems below an enrichment of 5%. Otherwise, you won't be able to do that. That's why you want to moderate the neutrons. In a fast system, you have to operate those systems with a much higher fissile concentration. It is no longer an enrichment per se, because you're taking new fuel, plutonium, for instance, and mix it with uranium, right? But at the same time, you are able, the physics that governs the fast neutrons says that you can actually fission almost everything. Okay. Whereas uranium-8, for instance, if you take uranium-8 or plutonium-240, which could not be fissioned with thermal neutrons, could actually be fissioned with fast neutrons. That is the idea. So you take that fuel that was produced in light water reactors, you create a new fuel by mixing this with depleted uranium, and you put this for another cycle in a fast reactor, and you simply create energy, and you also burn all those actinides and transform those to short-lived fission products.
That's amazing.
That's what I was trying to describe you in the car yesterday.
This is really because my understanding of what you guys do is minuscule, and I have these questions like this, where it's, if you're only using it for 3 cycles, why can't you use it for 1,000 cycles and then have 0 waste?
So even with fast reactors, you cannot do this indefinitely. It has to do with the safety characteristics, because each material that is produced, each actinide or each fission product that is produced in the system, eventually has a different characteristics on the operation of the reactor core. It has to do mainly with the safety characteristics. And what we typically denote as the reactivity coefficients, they are really highly dependent. So what we want to have in a normal system is, whenever your power goes up for any type of reason, inadvertent move of a control material, whatever it is, okay, and the power goes up, we don't want to interfere. We want the system to passively react to that increase in power and dampen the power, okay? And this is typically done through a proper design of the system. And we have different reactivity mechanisms, inherent reactivity mechanisms, by choosing the fuel, choosing the configuration of the system, and so on, that it would suppress that power increase immediately, okay? And if you are using this recycling process indefinitely, you would actually damage this. Plus, there is really no need to do this indefinitely. I mean, because at the end of the day, what you would be producing is a lot of fission products. You would need to separate the fission products from the actinides, putting them again, and you have residuals of those actinides. You don't really need to. I mean, the amounts of those, they don't really justify putting them back into the fast system for 10 times more and more and more.
It's completely fascinating. Anyone in the lay community knows.
No.
Don't know this is possible. They think 3 Mile Island is what nuclear reactors are. And that's the only way you can design them, or an RBMK Russian design. They don't know.
This is what we were saying before, right? And they were Gen 1 or Gen 2 reactors?
Which ones?
So like 3 Mile Island, right?
That was from the original pressurized water reactor.
So that was a Gen 1 reactor, right?
I would call that. It's old. It's old Babcock and Wilcox.
Yeah. So now we are referring to, like, I guess, generation 3 plus. This is sort of like the intermediate. So generation 4 reactors are all the advanced systems that could essentially be also coupled with different energy, simply because of their characteristics, like high operational temperatures, for instance, low pressure. So they are typically considered to be safer, more economic. And there are a lot of challenges there as well to design the system in terms of not challenges that could not be overcome. Of course, we can design such a system, but they are not mature as light water reactors.
Yes.
Okay, I mean, you have so much experience with light water reactor systems that I don't think you'll be able to achieve the same with fast systems, for instance, at least now. But in the future, those would kick in. I guess now a lot of discussion goes towards small modular reactors and micro reactors. I think the later, the micro reactors, are the new, I guess, hot stuff in the market right now.
Yeah, I mean, we've been talking a lot about small modular reactors.
Smaller versions of the light water reactors, right? Boiling or pressurized, either way, they're smaller.
Yeah.
And now you have the micro, which becomes.
Talk about a micro reactor. My understanding is an SMR is, about the size of a postbox, right?
Yes.
So micro is now how big? The size of my phone?
No. Small modular reactors are still fairly big.
They're
fairly big.
Yeah.
And that's a broad definition of how big they are. Actually, they can be even too big. But take a light water reactor, a basic light water reactor. One of the main issues is that you have steam generators and you have a pressurizer and so on. And you have the main pressure vessel that holds the internal components of the core and so on, right? But at the end of the day, water that flows to cool down the system, it flows from externally to internally, right? And, you could have, for instance, scenarios associated with breaking a certain pipe. And then how would the core behave after that will happen? So the idea of small modular reactor, how about we create this pressure vessel and put everything inside the pressure vessel? Obviously, creating this pressure vessel is not impossible. I mean, there's manufacturing constraints, so you cannot make it as big as possible. It's not constrained. So small modular reactors are typically below 300 megawatt electric. Okay, where a big system is around 12. It depends.
1,200 years.
Yeah, French systems now is like 1,500
Yeah.
megawatt electric.
Yeah.
And a small modular reactor is built under the concept that everything is integrated within the system. So even if something breaks within the system, the water is still there.
Everything's in there.
So you never expose the core, for instance. So you eliminate some of the
Safety risks.
Exactly. By inherently designing the system in such a way. Small modular reactors, for instance, if you take, I think NuScale is also considered to be a small modular reactor. It's much smaller. I think it's, 70 megawatt electric, roughly.
Yeah.
It would actually be fairly big, not radially big, but in axially big. Why is that? Because it relies on natural circulation, and that's why you need to be tall. Yeah.
So the one that I was looking at the other day, the B.W.W 300 from GE, they were saying that it uses a lot of that gravity to pull things down. So this is
that's a small.
That's GE's SMR. I was listening to some stuff about it, and they were saying that it uses the gravity to help with that. And I was trying to get an idea of like how big it is.
It's big. It's tall. It's not big. It's very tall.
Yeah,
it's very tall. But the idea is that in any scenario, what you have is natural circulation. So you don't need pumps, for instance, or you don't need electrical supply if something happens.
And has that got to do with the fact because it's a boiling water reactor, as that water boils, it just naturally condenses and drops back down?
Well, it is associated with density changes as well. So
and that affects where it boils in the core, but that's really a separate issue.
Yeah.
The fact that it's boiling is really just another different. I think it's really saving I think it's a separate issue.
It is slightly different.
Yeah,
it's more complicated. But the idea is that you will have a natural circulation of the cooling phenomena. You would convect heat naturally without any active components. And the idea with small modular reactors was, first of all, let's make them safer, integral in one system. That's one. And number two, traditionally at least, I think when we started building reactors, of course I was not here, but they were actually small first, and then they got bigger. And the idea of why we want to make things bigger is simply
like Yankee in Massachusetts was the first one, and it was tiny.
Yep. But you want to make the reactors bigger simply because you have the economy of scale. I mean, bigger things cost less per the energy produced, right?
Right.
And that was the idea. And recently what happened is you have a lot of delays in constructing those. And we don't build enough reactors, in my opinion, nowadays. So what happens, you don't have that the same crew is not building this another reactor. So there is no real learning curve there.
Yeah.
And so the idea of small modular reactors, the way I understood it initially, is that you will be able to build more of those and increase your learning curves and employ what we call mass production or economy by mass production.
Yeah.
Do you have a sense of how many of those SMRs have been produced around the world, have made around there? Is it all still just design? It's all design.
They're all designed. So the new scale is really the first.
Yeah.
And so when we talk about microreactors, how big are we talking about with microreactors?
And again, there are multiple microreactors. For instance, my group is focusing on reactors. This is just an example. There won't be completely different. So we are designing something completely different right now, which is still academic research. It's a very low readiness level technology, but at the same time, in my opinion, has a very disruptive impact at the end of the day. So this thing that we are designing is like a meter in diameter. So let's say something like this. And actually, it could be quite tall, but still...
8 meters or 3?
No, probably 5 meters.
5 meters.
5 meters, you can still transport it by truck. Okay, and actually that would be a full module. So this would produce a relatively low power. Microreactors, by the way, they don't have to be 5 meters long or so, but the heat pipe reactor would be similar in size, I guess. Maybe...
You get to 40% efficiency on it, okay.
It's I'm exaggerating.
Okay, I thought it was 35. Okay,
it could be 30%.
Yeah, 30.
But the idea is we are actually what we do in my lab. We are at the moment heavily involved in 2 projects. One that I'll be more than happy to tell you about is how we send crewed mission to Mars.
We want to talk about that.
I definitely want to talk about it. And that's my fascination.
Something that I personally didn't know anything about 3 years ago, and now
now you're an expert.
I think now that my group at least in the United States, we do a lot of nice work. We have ties to BWXT as well. Not necessarily we are connected through a student, but anyhow, for the microreactor of this nature, we are actually trying to come up with a completely different power conversion system. So typically what you have in any system, doesn't matter if it's a small modular reactor, large reactor, or a microreactor, you would convect heat using fluids, essentially. We do not need any fluids. We don't have any pumps. What we have is we
do conduction?
No, we do convective radiation.
Convective radiation. Why radiation?
So we heat up, and it's very simple. So we are trying to simplify eventually our design and make it super economical as well. So we will heat this. We have this.
Well, that's why I work in space, because you use radiation.
So it doesn't have to be. Actually, this is also for mass production as well, because we envision the system eventually, maybe not today, but maybe 20 years from now or 10 years from now, to be produced in factories using like standard manufacturing to produce just the block. It will be surrounded by thermophotovoltaic cells. And there is an emitter here that is heated to fairly large temperatures, 1,000 degrees C, but something that is still fairly comparable to standard systems. And once this is heated to high temperatures, it will irradiate photons. Those photons would be absorbed by the thermophotovoltaic cells, and those that are in specific energies would actually be reflected back to the core. So we're not necessarily losing energy, we are recycling the photon energy as well. This is not a completely new or revolutionary idea. That idea was somewhat similar to what was proposed in a space program, but they didn't use a critical core. They use, I guess, like plutonium-based generators.
Yes.
We are producing.
That's a critical core, though.
We are producing with a critical core. Power levels are very small, meaning this core will produce around 1 megawatt electric. Okay, so it's fairly small compared to, as I said, a system that produces 12,000. But what are the advantages here? If we are right and we can produce thousands of those, then the learning curves of this technology could be, I guess, increased to 18, 70%, as you would see in flight industry and so on. So I think this is
1 megawatt running all the time would make a lot of power.
No, I agree. So,
Power like a campus or something.
so for instance, remote locations,
half the size of power plants.
remote locations, military applications, space applications. This is ideal. If I look, so now at this point, this is designed as a niche application. Okay, it is still economically competitive if you compare this to, let's say, take Alaska for instance, where they use diesel generators, right? So this would still be competitive, very competitive.
Yeah, you could put one into your home.
I don't think you need
need
one
it.
for
You need one for like Olive Golden Oak.
Yep.
Oh, for like the whole of Alaska.
Yeah.
For like one whole section. Or you could put 5 into a whole town. Or
So
something.
you could put like 1 or 2 into a town.
Yeah, that's like,
Yeah.
Yeah.
Now,
you just distribute this around where it's needed instead of having this central plant.
I don't want to say that typically the way nuclear reactors are being designed is from the core outside, typically. So in this specific case, this is a multidisciplinary project that we actually involve a lot of, I guess that's why Georgia Tech is so great. We have mechanical engineering, electrical engineering. We actually met, and this was a design through conversation, which was very nice. And
Multidisciplinary design.
Yeah, multidisciplinary design. And recently, the main idea with thermal photovoltaics, for instance, is that their efficiency was historically very low, below 10%, not very economically viable.
Yeah.
And we recently partnered up with an industry company who are sort of new, and they demonstrated an efficiency between 30 and 40%, which is unbelievable. They broke their own records in presenting that the efficiency could be as high. So you can actually efficiently convert the thermal energy to electrical, which is great. Again, there are a lot of microreactors concept. I'll just some of the key features of why microreactors are so important. You cannot break them. It's a walk-away feature, meaning because they're small, because the power density is relatively small, you don't need to do anything. They will be cooled down by themselves. There's no intervention, and I guess, and that's a field that I myself don't have a lot of experience there, but they can, because of their inherently passive features, they could be easily autonomously controlled. And I think this is where we go with this field now.
That's cool.
Yeah, I mean,
that's what you want, isn't it?
Yeah.
That's how you probe into deep space.
Yeah, well, that's not only how you probe deep space, but it's how you sort of change the game in remote areas of the planet.
Yes.
Well, I don't know if you've heard
Yes.
that recently NASA, they are discussing the option of putting a fission power
On the moon.
On the moon. Because of the lower gravity than the Earth, they are planning to use it as a hub to launch different missions. Which makes sense.
a lot of sense, yes.
So,
Because then you don't have the cost in
fuel.
getting out of Earth's orbit, right?
Yeah, it's easy to get out. Once the escape velocity is low, right?
Yep.
Super low.
So such systems could be, it doesn't have to be the specific system.
But you could tweak that and optimize it for that application.
I think
Well, not only that, it's probably easier to build a bunch of those on the moon than it is to build a bigger reactor.
You couldn't build the kind of reactors.
I don't think you can build the big reactors, and I think it's more about resources.
What I'm talking about is, imagine you had a way station there, and you could actually facilitate the production of those on the moon.
Oh, yeah.
So then,
Yeah.
when you were doing missions to Mars and beyond,
Titan or wherever.
Yep.
you just take up the raw materials to make it. You actually do the assemblage.
Yes,
on
but the moon is where you do it, yes.
Yeah,
Yeah.
And then you need to worry about the health physics of the workers on the moon because they don't have an atmosphere.
correct.
All right.
But then, as I learned this morning, we put up a big shadow shield, and they just work and live
Well,
in the
that helps
shadow
them from the reactor, but doesn't help you from the sun. Put them underground, right?
Yeah.
Put them in a building.
You don't want to get what's that the regolith. You don't want that up in your ears and stuff.
So that's interesting, Dan.
Again, recently maybe the last part that I'll tell you about is this nuclear thermal propulsion engine. This is really just an indication why nuclear energy is so important. Because I don't think you can reach such performance with any other energies. Like nuclear in this specific case for applications in remote or applications in space, this is probably the only way to go.
Only way you can do it.
Yep.
Yeah.
And I believe nuclear thermal propulsion engine, still big, but at the same time can take actually the next crewed mission to Mars, which is unbelievable. And so the idea, a nuclear thermal propulsion engine, because it's a high power density source and it does not need an oxidizer, then you can really.
That's all the weight.
That's really the weight. I don't know if you've seen the big engines.
Oh yeah.
This is the engine, and this is the tank of the propellant.
Yeah.
Right? And
look at the old space shuttle. It used to it had the two boosters.
Yep.
And then you had literally the big orange tank in the middle.
I'm glad this came up. Because this is a concept I'm trying to put words to. Maybe you have better words than me. But I'm trying to give someone like this who does movies, who's interested in science technology but didn't really study it, a concept of the world that humans have lived on to get from monkeys or whatever to where we are kind of modern now is at the outer shell electron level. Burning things, oxidizing things. That's just changing chemical bonds with the outer shell electrons among stable, not radioactive, but stable atoms, correct?
Yeah.
And those are roughly EV level, they're electron volt level energies, changes. So they're in this level, we'll call them EV, just some unit of energy. But when you break a bond, it's several EV or maybe hundreds of EV or maybe even 1,000 EV, but not much more than that, right?
That's right.
Okay, so this is 1,000 units of energy, and the whole world, our bodies, the mitochondria burn that rate to make us warm. Everything we do in the world is just EV level. This shit is 220 MeV level. It's 10 to the 8th different.
Yeah.
Okay, so which one do you think is going to work? But that's not, people don't know that.
Yeah.
Why is it different? Because you're using a different bonding process to that.
How are things going?
Good. Yeah, they're going really well.
All right.
We're about to start geeking out over Mars projects in a minute.
Okay. You're talking about propulsion?
He's got him on propulsion now.
This is, right. Nuclear thermal propulsion, NTP. Okay, cool. I just want to check in and see what you guys were up to, and again, whether or not it was worth how much longer you'd be.
Not much longer. Yeah, if you want to. I was just trying to say, maybe for the podcast as a concept, I think, humans are aware of EV level transitions.
Yeah.
Because those are burning fossil fuels, burning of firewood.
Yeah.
Making rubber for a car tire.
Yeah.
Everything commercially that you know of, except for a few things you don't know of for radiation involved, is EV level stuff. And that's so there's the four fundamental forces of nature. And we're right, that's the Coulombic interaction.
Yeah.
That's just one. That's the weakest
million
one.
Times higher.
Millions
energy.
Yeah. So what we're saying is we're moving away from being monkeys. You need to move on into the higher energy sources and use those intelligently. That's what nuclear engineering is really trying to do.
Yeah.
And that's what it's just not. You can't get there because of all the people that suck at the EV level. That's conceptual for you for the movie. I think that's a good concept to think about. It also educates the audience about four fundamental forces of nature, and they don't even know what they are.
Yeah. Well, yeah.
So just for reference, typical chemical rocket would be twice as slow as a nuclear thermal propulsion, and it won't have as many options to travel. So you have different time points where you can actually travel because Mars and Earth are moving different orbits.
Yeah. Because Mars is in its elliptical orbit, so you've got to wait till it gets to that close point. Make sure you're intercepting it in that orbit to put a man on Mars.
Yeah, right.
So according to if
we can move double as fast using 1/1000th the weight, why don't we do that?
That's exactly what we are planning to do. And so nuclear thermal propulsion has now become a very, hot topic in the community. And there is a lot of funding, from NASA. But also, now you have Blue Origin and Lockheed Martin that are involved also in the spacecraft design as well.
Yeah.
So there are a lot of...
and does SpaceX get involved with that as well?
Yes, SpaceX is involved in that as well.
Yeah. Amazing.
Yeah, some of that is Department of Defense projects, and some are directly funded from NASA now.
Yeah.
But there is a lot of talk about sending a crewed mission to Mars, and I guess the only really viable option would be using a nuclear thermal propulsion engine.
Yeah.
There's no way to get it back if you don't.
Yeah, that's true.
They're going to go there and die, so you have to send coffins with them.
Yeah.
Which, if you think about, is not a new stuff. That's a microreactor there.
Yeah.
I can call it easily a gas-cooled microreactor.
Yes.
It's small. The only difference is that it operates at a much higher temperature. That's not a negligible, but you have to bring the propellant to a very high temperature because the exit of the velocity of that propellant from the nozzle depends on the chamber temperature. So you have to heat it to a very high point.
Yeah.
It's the delta T, the delta temperature is what gives it the energy.
Yeah. But this also allows us, there is a lot of advancement in that specific field, which I think will be translated into civil applications as well eventually, because a lot of the material design to be high temperature applicable is being studied for those concepts right now as well.
I can't wait to get into more of that with you. I think there's a lot to be said, not just for Mars, but everywhere else as well, everywhere that's not Earth.
Yeah, you think about how do I manage what I know to be the only fundamental forces that I can manage.
Yeah, well,
this is the only way you can do it.
Well, the bit I'm latching onto is we talked about it doubles the speed. Well, how do we double that again and double that again?
Yeah.
And have an exponential doubling of speeds until we get to like some real speeds where we can, exit our solar system.
So
with people.
Yeah.
There are advanced concepts. I think they're too advanced at this point, but they're talking about actually increasing this by a factor of 5 from where we now right now.
Yeah.
It's using a plasma, but I won't get into the details because I'm really not an expert there. But
yeah, it's very interesting. Well, thank you so much for your time.
You're welcome.
It's been fascinating.
We may have follow-up questions. We will just reach out to you.
We will definitely have follow-ups. If he doesn't, I will. Perfect. I may sound like an idiot while I'm doing it, but
just send the questions in Hebrew.
And you answer in Hebrew.
All right.
Thanks for listening. And remember, you can find the Coefficient Life podcast on Apple Podcasts, Spotify, or wherever you listen to your podcasts. If you have a topic you want to hear more about, follow us on social media and message us through Facebook. Remember, energy is everywhere. Use yours wisely.